Good morning, everyone. I am delighted to welcome you all today. Thank you for joining this presentation. Today, we will be discussing the validation of disinfectants. The presentation is titled Validation of Disinfectant, and I will also touch upon related aspects to give you a comprehensive overview. Over the next few slides, we'll explore the importance of disinfectant validation, the methods involved, and key takeaways. Let's get started. Let's start by understanding what disinfectant validation really means. Essentially, it's a documented study that confirms whether a disinfectant is effective against specific microorganisms. This isn't just a general test. It's conducted under defined conditions like the right concentration, the necessary contact time, and on particular surfaces. Now, why is this important? Well, the main objective is to demonstrate that the disinfectants we select actually work against microorganisms in our environment. We need that assurance to keep our manufacturing areas safe and microbial control consistent. And of course, there are regulatory requirements we must meet, like GMP or good manufacturing practices, that mandate proper validation. So, in essence, disinfectant validation is a critical part of ensuring product safety and compliance, and it ties directly into our overall goal of maintaining high-quality standards in our facilities. Let's take a closer look at some of the key regulatory guidelines that underpin sterile medicinal product manufacturing. First, we have the EU GMP, specifically Annex 1, which provides comprehensive requirements for the manufacture of sterile products within the European Union. It's essential because it sets the standards for aseptic processing, cleanroom environments, and contamination control. Moving on, the WHO GMP also offers valuable guidance, especially for global consistency and best practices in sterile manufacturing. It emphasizes risk management and quality assurance throughout the process. Then there's USB 1072, which focuses on disinfectants and antiseptics. Proper use of these agents is critical for maintaining microbial control on surfaces and equipment, ensuring product safety. ISO 14698 is another important standard that deals with microbiological control in cleanrooms. It guides us on monitoring and controlling microbial contamination in controlled environments, which is fundamental to aseptic processing. Lastly, the FDA Aseptic Processing Guidance provides insights specific to the United States, emphasizing validation, environmental monitoring, and personnel practices to ensure aseptic conditions. All these references together form a robust framework that guides us in maintaining the highest standards of quality and safety in sterile manufacturing. They connect to the overall theme of our presentation, which is about understanding and implementing best practices to prevent contamination and ensure product integrity. Now, let's take a closer look at the scope of our validation process. Here, we're focusing on both routine disinfectants and rotation disinfectants. It's important to validate these disinfectants to ensure they are effective and reliable in maintaining our cleanroom environments. This validation applies across various areas, including all grades of cleanrooms, grades A, B, C, and D, so no matter the cleanliness level, our disinfectants need to perform consistently. We also need to validate their effectiveness on different surfaces, such as equipment surfaces, floors, walls, and workbenches. Each of these surfaces plays a critical role in maintaining a sterile environment, so thorough validation across all these areas ensures comprehensive cleanliness and safety. Ultimately, this scope helps us ensure that every step we take in disinfectant validation supports our overarching goal, maintaining the highest standards of cleanliness and ensuring product integrity. In selecting microorganisms for our study, we based our choices on several important factors. First, we looked at environmental monitoring trends, which help us understand which microbes are most relevant in real-world settings. We also considered regulatory expectations, ensuring our work aligns with industry standards and guidelines. Additionally, resistance profiles were a key factor, as we want to include organisms that pose challenges due to their resistance to disinfectants or antibiotics. Now, when it comes to the typical organisms we focus on, you'll notice a mix of bacteria, fungi, and yeasts. For bacteria, we have Staphylococcus aureus, which is gram-positive, and Escherichia coli, a gram-negative. We also include Pseudomonas aeruginosa, known for its resilience and impact in healthcare environments. Bacillus subtilis is on the list because it's a spore-forming bacterium, which makes it particularly resistant to certain sterilization methods. On the fungi side, Candida albicans is a common yeast that we often encounter, especially in immunocompromised patients. Lastly, Aspergillus niger represents mold species that can be problematic in various settings. By selecting this diverse group of microorganisms, we ensure our testing is comprehensive and relevant to the real-world challenges we aim to address. This approach ties directly into our overall goal of improving sterilization and disinfection processes across different environments. Let's take a closer look at the selection of disinfectants. When choosing the right disinfectant, it's important to consider its effectiveness against specific pathogens, as well as the surface or material you're treating. Different disinfectants work better for different situations, so understanding their properties is key. For example, some disinfectants are broad-spectrum and can target a wide range of microorganisms, making them versatile choices for general cleaning. Others may be more specialized, effective against certain bacteria or viruses. It's also crucial to consider safety aspects, such as toxicity and compatibility with surfaces, to prevent damage or health risks. Proper contact time is another critical factor. Disinfectants need to stay on the surface long enough to be effective. Overall, selecting the right disinfectant is about balancing effectiveness, safety, and practicality, which ties into our larger goal of maintaining a safe and hygienic environment. Let's take a closer look at the acceptance criteria for our disinfection validation. We aim for at least a 3-log reduction in bacteria, which means a 1,000-fold decrease in bacterial count. For yeast and mold, we're targeting at least a 2-log reduction or a 100-fold decrease. If we're testing a sporicide, then we need to achieve at least a 3-log reduction in spores. These benchmarks are based on guidelines from USP 1072 and EU GMP expectations, ensuring our processes meet international standards. Now, moving on to our validation methodology, we use the surface challenge test. This involves several key steps. First, we prepare a microbial suspension with a concentration of around 105 to 106 colony-forming units, or CFUs. Then, we inoculate a defined surface area with this suspension. After allowing it to dry, we apply the disinfectant for the specified contact time. Following that, we neutralize the disinfectant to stop its action, and then recover and enumerate the remaining organisms. This process helps us accurately assess the disinfectant's effectiveness in real-world conditions, ensuring we meet the necessary microbial reduction standards. Overall, these criteria and methods are essential to validate that our disinfection processes are reliable and effective. Now, let's look at this example of test data. We used Staphylococcus aureus as our test organism. Initially, we had a count of 1.2 million colony-forming units, or CFUs, which gives us a baseline of how many bacteria were present before disinfection. After applying our disinfection process, the recovered count dropped significantly to about 1,100 CFUs. This reduction demonstrates the effectiveness of the disinfection method in lowering bacterial presence. It's important to note how this kind of data helps us evaluate and compare different disinfection techniques. Ultimately, this example illustrates the importance of quantifying bacterial reduction to ensure our methods are both effective and reliable, aligning with the overall goal of maintaining high standards of cleanliness and safety. All right, let's take a closer look at this table, which summarizes the results of our sporicidal validation example. Here, we've used Bacillus subtilis as our test organism, which is a common choice for sterilization testing. The initial count of bacteria before treatment was 5 × 10 to the power of 5 CFU, or colony-forming units. After the sterilization process, the recovered count dropped dramatically to 2 × 10 to the power of 2 CFU. Now, to understand how effective the sterilization was, we calculate the log reduction. We do this by taking the base 10 logarithm of the initial count, which gives us 5.7, and the logarithm of the recovered count, which is 2.3. The difference between these two values, which is 3.4, represents the log reduction. Since a log reduction of 3 or more is typically considered a pass in sterilization validation, this result confirms that our process was effective in reducing the bacterial count significantly. So, in summary, this example demonstrates a successful sporicidal validation, with a clear reduction in spores that meets our standards. This kind of data is crucial for proving that our sterilization process works reliably. Let's talk about revalidation now. Revalidation becomes necessary under certain conditions to ensure continued effectiveness and safety. For instance, if there's a change in the disinfectant being used, we need to revalidate to confirm it still meets our standards. Similarly, any change in the formulation of the disinfectant or cleaning process requires revalidation. We also need to be alert to adverse environmental monitoring trends, which could indicate a potential problem that warrants revalidation. To keep everything on track, we conduct periodic reviews. This review involves analyzing environmental monitoring data and looking for trends over time. By regularly reviewing these data points, we can identify issues early and ensure our sterilization processes remain reliable. This ongoing process is crucial because it helps us maintain high standards of safety and compliance throughout our operations. In conclusion, I want to highlight that all the disinfectants we tested met the regulatory acceptance criteria, which is really encouraging. This means they are reliable options for our disinfection needs. They are effective not just against bacteria, but also fungi and spores, which covers a broad spectrum of potential contaminants. Additionally, the validated contact times and concentrations we've established are suitable for routine use, making these disinfectants practical for everyday application. This supports our ongoing environmental control programs by providing proven, effective solutions. Overall, these results reinforce that we're using disinfectants that are both effective and compliant, helping us maintain a safe and clean environment consistently. For further support, please don't hesitate to reach out to us. We're here to help and provide any additional assistance you may need. You can contact us through the details provided, and we'll be happy to guide you. Thank you so much for your time and attention today. We truly appreciate your engagement and look forward to supporting you moving forward.